Hello everyone, I'm Hong Mei Chen from Yunnan University in China. The title of our paper is ESPM, Efficient Spatial Pattern Matching. Spatial Pattern Matching, SPM for short, uses a pattern to capture users' intention and aims to efficiently enumerate all the matches of the pattern from a set of spatial textual objects. Let's consider example in Figure 1. To find a residential area, a user may prefer a house, a park, and a station, where the park should be very close to the house, while the station should be close but not extremely close to the house, so that she can take buses conveniently but without suffering from loud noise and massive crowd in the station. Such requirements can be expressed as the spatial pattern in Figure 1b. Notice that the arrow from house to station means that there is no other station whose distance to the house is less than half a kilometer. Clearly, in Figure 1a, the three objects linked by dashed lines, that is H1, P1, S1, satisfy all the constraints in the pattern, and that's a match of the pattern. Note that the object set H2, P1, S1 doesn't match the pattern because there is another station S2 whose distance to H2 is less than half a kilometer, making it unsatisfying the pattern. SPM was first introduced by Fang et al. In ICDE 2018. Let's see the problem definition of SPM. A spatial pattern is a graph with both keyword and spatial constraints. Firstly, each vertex is labeled by a keyword, which represents the keyword of a matched object. Secondly, each edge is associated with the distance interval, which represents the lower and upper bounds of the distance between two matched objects. Thirdly, each edge is described by one of four sides. Different size represents different exclusive or inclusive relationship among two matched objects and other objects. Given an edge, an image is a pair of objects with the keywords of the edge, which satisfy the spatial constraint of the edge. Given a spatial pattern, a match is a set of objects. If there is a surjective mapping, such that for each edge, the surjective object pair is the image of the edge, then SPM problem can be defined as given a set of spatial textual objects and a spatial pattern, return all the matches of the pattern in the set of objects. SPM has been demonstrated to be useful but computationally intractable, that is NP-hard. The state-of-the-art solution is inefficient on large-scale datasets. To enhance the performance of SPM, in this paper, we propose a novel efficient spatial pattern matching algorithm, ESPM for short. We adopt the inverted linear quadtree index, IO quadtree for short, and compute matched node pairs and object pairs level by level in a top-down manner. In particular, we develop effective ordering strategies as well as pruning criteria to prune unpromising nodes and node pairs at the high levels, which make a large number of unpromising objects and object pairs to be pruned before accessing them from disk, making our algorithm much faster than existing algorithms. Our experimental results on real large datasets show that ESPM is over one order of magnitude faster than the state-of-the-art algorithm and also uses much less I/O cost. The ESPM algorithm follows a three-step framework. Firstly, it computes n matches for edges level by level in a top-down manner. Then it computes images for edges. Finally, it joins images to compute all the matches of the pattern. We first introduce the concept of n-match. Given an edge, a pair of nodes in the IL queries of the keywords of the edge is an n-match if they satisfy the following constraints. The edge with different sign has different constraints. For example, 1. For a mutually inclusive edge, if the minimum distance between the minimum bounding rectangles of two nodes is not larger than the upper bound, and the maximum distance between them is not smaller than the lower bound, the pair of nodes is an n-match. Note that a mutually exclusive edge can be converted into two exclusive edges. In step 1, we compute n-matches for all edges in the pattern, level by level in a top-down manner. The order of computing n-matches has significant effects on the computational efficiency. Nevertheless, it's costly to derive the optimal order, so we develop an efficient heuristic method to derive the order. Note that to enhance the pruning, the orders in different levels are dynamically adjusted. For each edge in the order, we prove unpromising nodes that do not contain objects in the matches of the pattern by using the n-matches of its adjacent edges. Then we compute the n-matches by using the n-matches in the previous level, which results in high efficiency. Similarly, we compute images of all edges except skip edges in step 2. We identify skip edges by using the order of computing images. Then we skip the computation of images of skip edges by checking object pairs in next step. In step 3, after deriving the order of joining images, we join images of non-skip edges and check object pair for skip edges to compute all the matches of the pattern. In experiments, we use 5 real data sets. Table 1 summarizes the statistics of these data sets. Following the method in reference 1, we use the 12 structure of spatial patterns and create 20 patterns for each structure. As a result, we have 240 patterns for each data set. In figure 2, we report the average response time and I/O cost for each pattern on each data set. Clearly, on all data sets, ESPM outperforms the state-of-the-art SPM algorithm, MSG, and is over one order of magnitude faster than MSG in terms of the response time. In particular, on the largest dataset, TW2, it's up to 132 times faster than MSG. Seen averagely, it takes about 5 seconds, while MSG takes about 11 minutes for a pattern. Meanwhile, the I/O cost of ESPM is much less than that of MSG on all the datasets. This is because ESPM uses effective ordering and pruning technique to prune unpromising nodes and node pairs at high levels of I/O query, which greatly reduces the overall running time. That's all. Thank you for your listening.